Hello again. So this is part of the things that I'm going to show you about the exercise program from this Monday. I've chosen to show you two of the exercises, that is exercise 1 and exercise 4, and they are both by hand. So let's start exercise 1. You have a vector field, and then you have a surface given by a parametric representation, and if you look at it, then this surface is the xz plane, as you can see here. The second coordinate is 0, so it's the xz plane, and you have that u varies between 0 and pi, and v varies between 0 and 2. In order to compute this flux, you need to have a normal vector to this surface, and you take the derivative of your parametric representation with respect to u, and then you cross it with the parametric or the v derivative of the parametric representation, and you get the 1, 0, 0 cross 0, 0, 1, and this is 0 minus 1, 0. Not surprisingly, it is pointing in the negative y direction, but being the xz plane, this is not surprising. In order to get the integral in your flux integral, you need to take the dot product between this normal vector and your vector field restricted to the parametric representation. So I put in this parametric representation in the vector field, and I get, and then I dot it. So you only have the second coordinate in your vector field, and you get cosine u plus cosine v with a negative sign. In order to get the flux, you integrate from 0 to 2 and from 0 to pi, the limits of your variables of du and dv, and then your integrand. And first you integrate with respect to u, you get, I put the minus sign outside the integration signs, and then I get the integral of cosine u, that is sine of u, and then cosine v is a constant, so it will be u times cosine v. Put in the limits, and sine of u makes no contribution, but you have a contribution here from pi times cosine v, put pi outside the integration, and you do the second integration, and you have this result. And you can see here from the answer that this is correct. Now, if you want to change the sign, or you are asked, is it possible to change the sign by altering the parametric representation? And it is. In fact, you could just interchange v and u in your representation, and then you will change the sign. You should try that. It goes along the same way, but you get a positive result. Now, in the question C, you have a bit more complicated vector field and a bit more complicated parametric representation, but the computations are more or less the same. You perform in the usual way the normal vector as this cross product. Take the derivative with respect to u of your parametric representation, and with respect to v, take the cross product. And when you've done so, you dot this cross product. You see here you have u sine squared of v plus u cosine squared of v, and this is u. And similarly, when you put in your representation in your vector field here, then you get this result here, and this is your integrand. Fairly simple, and you can do the flux integral, and now your limits of integration is 0 and 1, 0 and 1, and when you do this you get the result 3/8. Okay, now in exercise 4 you have a rather complicated vector field, but if you compute the divergence, then it's fairly simple. See, 2 plus x squared minus 2xz. This is the divergence, and your surface is the 6 surfaces, or you want to compute the flux through the 6 surfaces of a unit cube. But it is a cube with side lengths of 1, and being axis parallel, you can use x, y, and z as parameters. So it's fairly easy to write the flux integral. I've done it in this way here. You have the divergence, and you compute the integral from 0 to 1, and so forth. 2 gives you 2. This is 1/3, and then minus 1/2, and if you sum it up, you get 11 divided by 6. So let's go to number 4. You can show the hint. It's an axis parallel cube. You have the divergence, and this is the result. Well, in the next one you have a bit more complicated vector field, but the divergence is still simple. You get this this divergence, and this is your integrand in this spatial integral. You have the flux is equal to the spatial integral over the volume over the region capital omega of your divergence, which I've written here, and when you compute it you get this result here, and again this is similar to the result. The final question is that you're given this triple integral, and the question here is, can you find a vector field whose divergence is equal to this sum here? And it's fairly easy to postulate such an integral, because you see, if you take this as your vector field and compute the divergence, then you get x plus y plus z, and when you integrate you get the 3/2. So this vector field here, the flux of this vector field through the surface of this say again here, this unit cube is equal to 3/2. So this is all for this video. I will upload later this evening another video with exercise 5 of this of the Monday program. So thank you.